Okay, this video is cardiac action potential excitation coupling. And so we did part one yesterday, and it was called cardiac action potential for medical students. So today we're just going to go a little bit beyond that. So you have the action potential initially, and you have, we went through the number of the phases. 4 is resting potential with calcium exiting, with potassium exiting. That's what these lines for is potassium exiting. Then you get an influx. This is cytoplasm, this is extracellular matrix. Influx of sodium at phase 0. Depolarizes the cell. Resting membrane potential was -90. Threshold was 70 to fire the action potential of fast-acting voltage-gated sodium channels. Then here you're running the plateau phase at number 2 phase of the action potential, where you got an equal amount of calcium entering the cell and potassium exiting. Everything is color-coded. So red is for sodium, like the sodium channels you can see down here entering the cytoplasm. Again, this is extracellular matrix. You got the orange for calcium, you got the blue for potassium. Then the calcium channels close, and you just have continued potassium exit in the blue, and that's phase 3. And then you end up at your resting membrane potential phase 4. You mostly got leaky potassium channels at rest, such that the resting membrane potential of potassium channels is about -90, about -94 in that ballpark. And because they're the main thing leaking at rest, you'll have a resting membrane potential next to their equilibrium potential. So it's -90. All right. Now I'm going to get into something new. That was just a brief little review. Okay, so here's where it gets a little bit more interesting. All right, first of all, you've got gap junctions between the cardiac muscle cells. Cardiac muscle cells are called cardiomyocytes. So cardiac, myo for muscle, cyte for cell. Okay, the plasma membrane of a cardiac muscle cell is called the sarcolemma. The cytoplasm of a cardiac muscle cell is called the sarcoplasm. So just sarc kind of comes in front of everything with muscle cells. All right, then you have gap junctions that connect the cells and allow a small amount of positive ions to pass from one cell into the other. So these positive ions through the gap junctions are enough to get the resting membrane potential to be elevated. When you hit -70, so the baseline is -90 millivolts as a resting membrane potential. You hit -70, then you open up the voltage-gated fast-acting sodium channels. You fire a rapid upstroke action potential. You even go above 0. That's called the overshoot. You have an initial repolarization, tiny amount through potassium exit, and then you end up in equilibrium phase where potassium exit equals calcium entry. And that's a long plateau phase, especially in ventricular muscle of the heart. Now, this little invagination of the plasma membrane is called the T-tubule. And the T-tubule is sort of an expansion of the extracellular space, and it gets more calcium channels. These are VG for voltage-gated L-type calcium channel, LCC. It gets more calcium channels sort of deep into the more central parts of the cardiac muscle cell. And these allow calcium to enter the cell. This is this part of this plateau phase. And when this calcium enters the cytoplasm, the sarcoplasm of the cardiac muscle cell, it will bind to the RO receptor on the sarcoplasmic reticulum. The sarcoplasmic reticulum in cardiac muscle is really like the endoplasmic reticulum in other cells, but it's especially designed in cardiac muscle to store a lot of calcium. It binds to the calcium binding protein inside there called calsequestrin. So when this calcium that had come in from the extracellular space through the voltage-gated L-type, long-acting type calcium channels, it will bind to the RO, ryan-odine. Ryan is almost like two Irish names, Ryan and Odine, receptor calcium channel. And then this will cause the sarcoplasmic reticulum to release calcium into the sarcoplasm, the cytoplasm. All right, so this is called CICR. This means calcium induced, because it's induced by this calcium, calcium release, because calcium is being released. And this allows more calcium to come into that sarcoplasm. And the purpose of this is to get the muscle to contract. A relatively small amount of calcium that came in through the voltage-gated L-type calcium channels, that affects the membrane potential of this action potential, but for contraction, it's especially important. This is not enough to cause it to contract. This extra calcium coming out of the sarcoplasmic reticulum, and it will then bind with troponin C. There's troponin TIC. I just make a mnemonic tick. Okay, troponin C, the calcium will bind to that, and then that will cause a cascade of steps to get the cardiac muscle to contract, which includes the myosin thick filaments, the actin thin filaments, and the tropomyosin will move out of the way. It was blocking the contraction mechanism that involves the myosin heads. Okay, so that's what cardiac muscle contraction is about. Okay, I know there's always more detail. We're not going to go into any more detail on that. I'm mostly interested in understanding this calcium signaling and also how a cell magnifies its signal. So the next thing to be aware of is the cell has these baseline pumps that run like this typical, we know this one well from other times, and we've talked about this in other contexts, the sodium-potassium pump. This uses ATP in the membrane. It's always sort of pumping sodium out, potassium in. Okay? And then once the cell is done contracting, now the muscle is going to relax. You want to get that calcium out of the cell fast. So the calcium that had come in through the voltage-gated long type calcium channels is primarily removed from the cell through the knockout exchanger, also abbreviated NCX, whereby the electrochemical gradient is used to let sodium come in along its gradient and couple that. So you call this antiport. So you couple the inward motion of sodium to the outward motion of calcium. All right, this is very, very fast, this knockout exchanger. It's secondary active transport because the gradient for the electrochemical gradient of sodium was based on the sodium-potassium ATP pump over here. All right, you also have just a direct primary active transport pump here, plasma membrane calcium ATPase to pump calcium out that uses an ATP. Okay, so we got the basic idea here. And then here's something else that's rather interesting. We're going to talk about how the cell does things with stress. So here's stress. SANS means sympathetic autonomic nervous system. So that's fight or flight. That's what's activated when you're stressed out or you feel threatened by physical danger. Okay, and the classic metaphor to remember it is being chased by a tiger in the dark. So if you're going to be chased by a tiger, you need to run as fast as you can, maybe turn and fight, climb a tree or do something. So you need lots of blood glucose to have that energy. It also will raise your blood lipids a little bit. You don't need to worry about your immune system. All you need to do is try to survive the next 30 minutes with the tiger chasing you. So you shut everything off. You shut down the blood to the gut. You shut down the immune system. You're just focused on survival for that brief moment. And the catecholamines, hormones of the sympathetic autonomic nervous system, are epinephrine and norepinephrine. They'll bind to the beta-1 receptor. You can also call it adrenergic, beta-1 adrenergic receptor. And they will activate a G protein that's stimulatory. So I put G for S with a line through it to mean stimulatory. And then I drew an arrow here with a positive, meaning it activates this process of a plasma membrane bound or sarcolemma bound enzyme here, adenylate cyclase, which will convert ATP into cyclic AMP. And then cyclic AMP will activate protein kinases, and the protein kinases will phosphorylate voltage-gated long-acting calcium channels like the one over here, and they're going to cause more influx of calcium into the cardiac muscle cell. And that increased influx of calcium into the cardiac muscle cell is going to increase contraction. So that is the sympathetic effect. It also speeds up the heart rate. It does that in part by speeding up relaxation, but the important point is increase contraction and increase heart rate. So that's what you need when you're being chased by a tiger in the dark. Okay? And then the contrary, opposite, is parasympathetic autonomic nervous system, PANS. You can think of sympathetic as pushing your foot down on the accelerator. So this is accelerator is SANS, and then the brake is PANS. So PANS, the mnemonic for that is to feed and to breed, to rest and to digest. So you want to have more PANS in your life. We tend to have too much SANS in our life, okay? All right, so anyways, PANS, parasympathetic autonomic nervous system. It uses acetylcholine as, the hormone or the neurotransmitter, and it will bind to muscarinic receptor, and it will activate it, and it will cause inhibition of adenylate cyclase converting ATP to cyclic AMP, okay? So the important point is it does the opposite. It slows down contraction, and it decreases the force of contraction. So again, this is to feed and breed. So you're in parasympathetic when you're at rest. You're just taking it easy. You're going to have a nice meal. Everything is good, okay? So it's when you can relax. So you don't need a fast heart rate. You don't need increased force of contraction, okay? So again, what this does is it will increase contractility, increase speed of heart rate by letting more calcium into the cell. Okay, once the heart muscle is done contracting, then So that was systole. Now it's time for diastole. You want to get this calcium out of the cell. In a very big way, you get all this previous ryanodine receptor, the calcium-induced calcium release. This large amount of calcium, you get it out of the cytoplasm, out of the sarcoplasm, is you have it pumped back into the sarcoplasmic reticulum through the SERCA pump. So SERCA means sarcoplasm endoplasmic reticulum calcium ATPase. So that's a calcium pump, uses ATP, and it'll pump this calcium back into the sarcoplasmic reticulum. And that's how calcium is handled. And the reason why this is really useful is that these general ideas of taking an initial calcium signal and then amplifying it is very characteristic of a lot of reactions also in the brain. So it'll be worth your while if you're interested in these ion pumps and how this all works. It's always high concentrations of sodium and calcium in the extracellular space, like the ocean. Life came from the ocean. And then the cell will always have high potassium inside of itself as sort of like the counter ion. And then calcium is the aristocrat that makes things happen. So anyways, I thought that was kind of interesting, the alternative. This is the autonomic nervous system between SANS and PANS. SANS is the accelerator, PANS is the brake. So I hope you found that helpful.